Hello everyone. Welcome to the next lecture on the CSIR NET examination. Today, I will explain you how you can solve the problems related to the sequence of the functions. I cover all those questions from the 2011 to 2024. Again, I will explain you how you can solve this problem in a 15-second time. Myself, Dr. Harish Garg. You can follow my YouTube channel where you can find the playlist of the real analysis. And I assume that before watching this PY question series, you have watched already my theory lecture related to the sequences of the function. I already explained all those shortcut tricks in my this lecture. You must watch about my this series so that you can understand this lecture deeply. Apart from them, you can also watch the playlist of the CSR UGC NET, and you can see in this lecture I already explain detailed solution of all those questions asked in the 2024 and the other PY question series related to the group theory, calculus of variation, and many more available in this playlist. So let's start with this series. I can quickly recall the concept which I have defined in my this theory lecture playlist. So how you can check about the sequences of the function? The first concept whenever you are thinking about the sequence of the function is my pointwise convergence. Fine. And the second concept that we needed is my uniform convergence. How you can check about the pointwise convergence? You have to find the limit of the function. If this limit is my existence, whether it's a continuous or not, that is not an issue. But if the limit is my existence, then you can say the function fn converges to the f pointwise. Fine. Then we can say its sequence fn converges to the f pointwise. If the sequence of the function is not pointwise, then you can say directly it is not uniform convergent. How you can check about the uniform convergent? I have defined the three different methods in my theory lecture. Fine. In this lecture, I will explain you only with the one method called as the MN test. We can find the supremum over all those domain. If this Mn goes to the infinity, goes to the 0, then we can say Fn sequence converges to the F uniform. Again, as I told you, for more detail, you must watch about my uniform convergence, examples of the Mn test, pointwise convergence, and example of the pointwise convergence. These are very, very useful for you. Another, if you look about the shortcut tricks, look about these properties: boundedness, continuity, and uniform convergence of the differentiable. This lecture will be helpful for you when you look about this in sequences of the function. Now, if you're new to my YouTube video, you can scan and join my WhatsApp group as well. But make sure you are the part of the CSIR NET or the GATE examination, then only you can allow to enter in this group. Now, whenever there is a question related to the sequences of the function, fine, fn is defined to be x raised to power 1 over n. Your first target is to calculate the limit as n approaches infinity. So what will be the limit? What is the domain is? Since the domain is my closed interval 0, 1, so I can consider three cases: when x is 0, when x is 1, and when x is lies between 0 and 1. So clearly say when x is my 0, this function is my 0. When x is equal to 1, this value will be my 1. And when x is lies between 0 and 1, and this limit is my 1. Why? Because we all know limit n up raised to power 1 by n converges to the 1 as n approaches infinity. So any number which are lies between 0 and 1, I can consider as a 1 over n. If I substitute this number, it is 1 over. Now if you consider the limit as n approaches infinity, this is my 1 over 1. Fine. Now these are the limits. Now clearly say in all the cases, in all these cases, the limit existence. So therefore, fn converges to the pointwise, but they are not asked. Is this function is continuous? Clearly say this is not continuous, because at x is equal to 1 and x is equal to, at x is equal to 1, otherwise at 0, you can see this function is not continuous at x is equal to 0. So you can see it's define a continuous function. Cancel. Once the function, you can see fn converges to the f pointwise, and what is the shortcut tricks? As I mentioned you, if this function is my discontinuous, then this implies fn does not converge to the f uniformly. So this third option is also cancelled. Fn converges uniformly wrong because f is my discontinuous function. Limit of the fn is 0 for all x. Clearly say this is not for all x. Limit of the fn existence, yes, you can see because in all these three cases, limit is my existence. The first answer is my correct. Look at the second question. Again, your target is to compute the limit as n approaches infinity. I have the three cases again. If x is 0, if x is 1 over n, if x is lies between 0 to 1 over n. And the last case, when x is lies between 0 to 1, the answer is in the last case is a 0. If x is equal to 0, clearly say the limit is my 1. If x is equal to 1 over n, then the limit will be 0. If x is lies between 0 and 1 by n, answer is again 0. Fine. Now what will be there? You can see all these limits are existence. Fine. So the limit existence for all x, fine. Limit is 0, cancel. Is it a continuous function? Clearly say this function is my discontinuous at the point. Again, x is equal to 0. At x is equal to 0 is a 1. On the left hand line is a 0. So clearly say fn converges to the f pointwise. That's true. But this f is my discontinuous function. If this is discontinuous, then fn does not converges to the f uniformly. So this option is also cancelled. Is it a continuous function? No. So the right answer is only D is my correct answer. Look at this another one. Again, your target is to compute the limit. What is my domain is 1 and 2. I can say x is my 1, x is my 2, x is lies between 1 and 2. What is the limit when x is equal to 1? If x is equal to 1, the answer is my 1. If x is equal to 2, the answer is 0. If x is lies between 1 and 2, fine. So this limit, that means 2 minus x is lies between 0 and 1, fine. So when any number is lies between 0 and 1, if you take the n approaches infinity, this limit will be my 0, fine. So clearly say this function is my discontinuous at x is equal to 1. So f is my continuous function, wrong, because this is my f. F converges uniformly, again wrong, because fn converges to the f pointwise. But this f is my discontinuous, so therefore this option is cancelled. Now look at the third option. Limit 0 to 1 to 2 of fn. So if I look at the left hand side, what is the limit of the left hand side? Fn is my 2 minus x raised to power n. So what is the answer of this? It is with respect to x, it is n plus 1 over minus of n plus 1. Limit from 1 to 2. If I substitute 2 is a 0. If I substitute 1, it is 1 over. And it goes to the 0 as n approaches infinity. Look at the right hand side. It is 1 to 2 fx. What is the limit of when x lies between 1 and 2? Is my 0. So both are same. Yes, this option is correct option. Look at the last option. If for any a which are lies between 1 and 2, you can choose any a. Let's say 1.5. Fine. Then fn dash. Can you calculate the derivative of this? It is my n 2 minus x raised to power n minus 1 and negative a. If I choose a is my 1.5, then this number is my minus 5. It's a 0.5, that is a 1 over 2 raised to power n minus 1. I can say it's a minus of 2n divided by 2 raised to power n. Take limit as n approaches infinity. Clearly say it goes to the 0. You can see it's a infinity by infinity form. You can apply the L'Hopital rule. Again, you can see this will goes to the 0. So the left hand side is my 0. What is the right hand side? What is the f of x when limit is the open interval 0? So what is the f of 1.5 is also 0. So you can see both are my equal, but he said not equal. So this option is again cancelled. C option is my right answer of this problem. Look at this another one. consider which of, I hope you can like and comment on this video as well. Don't forget to subscribe my YouTube channel also. Which one of the following statement is my true statement? Again, your fnx is my 1 over n square plus x square. The function is monotonic, monotonic and monotonic. Remember, this is the sequence of the function. Fine. And once the sequence of the function, this is a monotonic with respect to the n, not with respect to the x. How you can check? You can find the derivative with respect to the n. It is my minus of 2n divided by n square plus x square of whole square. Clearly say this is less than 0 for all x. So what does it mean? The sequence of the function is my decreasing. Decreasing means that is my monotonic. Second option said not monotonic. Last option said not monotonic. Cancel. Now, whether it is a convergent to the 0 as the limit. So that means your target is to find limit of the fnx as x approaches, as n approaches 0. So clearly say when you take the limit as n approaches 0, n approaches infinity, this is always 0. But he said 1 over x square. This option is cancelled. Only first option is my right answer of this problem. You can see there is nothing you have to written. Just try to understand your calculation in your mind. Consider the function fn, then uniform convergence. So firstly your target is to find this limit. X is 0, x is my non-zero. Fine. What will happen if x is 0? Answer is 0. If x is my non-zero, I can write this number is e raised to power n x square as n approaches infinity. The numerator is independent of the n. So this limit will go to the 0 because e raised to power infinity is 0. So clearly say this function is my continuous. And in both the cases the limits are existent. So I can say fn converges to the f pointwise. Fine. Also we can say this function is my continuous. So once this is continuous, then you can never say that this will converges to the uniformly. You can never say. It may or may not be. But if this is my discontinuous, then definitely it will not converge. Then the question arises is how you can check about whether it's a convergent, uniform convergent or not. I can apply the MN test. That means supremum of all those x in the domain, fnx minus fx. Fx is my 0. So that means we need to find the supremum of x e raised to power minus nx square. Fine. Now how you can find the supremum? That's a very simple. If I consider y is my x e raised to power minus nx square, then I can find the first derivative to be 0. So if I take the derivative, fine, I can take it as a common, minus 2 and x square is my 0. That means x will be my plus minus 1 over root 2n. How you can find the maxima? Either you can find the second derivative. Otherwise, if you already watch my this lecture, uniform convergence, example of the uniform convergence, you have learned the shortcut tricks. This is my plus 1 by root 2n. Fine. So since this number is my positive, so 0 lies somewhere here. So if x is my 0, what is the sign of the, what is the sign of this? It is my positive. If x is any say larger number, say 100, if x is 100, this number will be my less than, it is my negative. So once this is my negative, that means this number is my maximum. And my target is to find the supremum. On the other hand, if you want to calculate the value at minus 1 by root 2n, so clearly say 0 lies here, it is my positive, and negative is my this number. So clearly say this point is my minimum. Since we need a supremum, so I can substitute the value of the x is 1 over root 2n in this expression. And we will see whether it will go to the 0 or not. 1 over root 2n e raised to power minus half. Clearly say it goes to the 0 as n approaches infinity. What does it mean? Fn converges to the f uniformly for all x belongs to the domain. So the first option is correct option. If Fn converges to the f uniformly on the R, it means Fn converges to the F uniformly on the closed interval a comma b, open interval a comma b as well. But he said only. Fine. So that means this option is cancel. Is not uniform convergent, cancel. The sequence is a bounded or unbounded function. So again, you can see this function is my bounded. Fine. Why? Because you can see that if x approaches positive infinity or minus infinity, this will goes to the 0. Therefore, it is my bounded, but he said unbounded. Right option is only A is the correct answer. I hope student you like and comment on these videos. Okay, now you can see this is the recent year paper 2024. Fx is f is a function from 0, 1 to semi-open interval such that f of x is my 1 over 1 minus x. Define the sequence p and x which of the following statement are true. Remember the options, they are talking about the uniform continuous, not for the uniform convergent. What is the tips as I given you in my uniform convergent lecture or uniform continuous lecture? If you watch about my this PY question series, if you look about the uniform continuous, fine. If you watch my this lecture, what is the shortcut tricks? As I told you, once you have the interval, your target is to find limit of the 1 negative of the fx existence, limit x approaches 0 positive fx existence. Once the endpoint interval existence, then we can say it is a uniform continuous. But clearly say, if you consider the limit x approaches 1 minus of 1 minus x, clearly say this limit does not exist. Fine. So that means the function is not uniform continuous. Fine. So the first option is the correct option. Now, second option is they are talking about the pointwise convergence. So clearly say this sequence is my GP series. I can found the sum of the series is 1 minus x. Then you can find the limit of the p and x. What will happen? The domain is 0 to 1. So if you take the limit as n approaches infinity, x belongs to the 0, 1. So this limit will be my 0 over 1 minus x. And clearly say it is my 1 over 1 minus x, which is nothing but fx. So you can say p and x converges to the fx pointwise. Fine. So second option is the correct option. Now, clearly say because f is my not uniform continuous. What does it mean? F is my not continuous. That means f is my discontinuous function. So if f is my discontinuous function, what does it mean? Pn does not converges to the f uniformly on the interval of 0, 1 because this function is not continuous at x is equal to 1. So sequence converges uniformly on the 0, 1 is a cancel. Last one, does the sequence converges on the closed interval 0, 1 where C doesn't lies of this? Then we have to apply the MN test, that is supremum of Pnx minus Fx. So if you subtract them, 1 over x minus 1 will be cancelled out. It's a closed interval 0, C. It is x raised to power n over 1 minus x. Now clearly say you have to find the supremum. It is occurring at the point C, and C is lies between 0 and 1, which goes to the 0 as n approaches infinity. Why? Because C raised to power n will goes to the 0 because C is lies between 0 and 1. So therefore Mn goes to the 0, hence Fn converges to the F uniform. So this is also the correct option. A, B and D are my correct answer of this problem. Okay, which of the following statement is my true? Again, you have to firstly find the series. Domain is my x is greater than equal to 0. I can choose the two cases. What is the limit if x is equal to 0? If x is 0, gx is 0, so the limit is also 0. Fine. If x is my non-zero, then the limit is infinity by infinity form. I can apply the L'Hopital rule. It is a x over 2 and x. So clearly say when n approaches infinity, this goes to the 0. So and this limit is existence. So Gn converges to the 0 pointwise. Fine. So Gn converges to the x, Gn converges to x, wrong. Now whether it's a pointwise, fine, but not uniform or uniform. So I will tell you the two methods. First method that is used only for the contradictory, not for the proof them. You can choose any x, any subsequence. You can choose any subsequence in this domain. I choose the one subsequence 1 over n. Fine. It's a subsequence. Fine. And if you prove that the subsequence f and k does not goes to the 0, then it is not uniform. It not converges uniformly. It is not uniformly converges. Fine. Make sure this concept is used only for contradict the options. Fine. Only to discard the option. Now my domain is this. If I use this subsequence, x is 1 over n. What is my g of subsequence? 1 over 1 plus 1. This is 1 over 2, which is not goes to the 0 as n approaches infinity. So therefore, g of n does not converges to the 0 uniform. Fine. So not uniform, correct option. This option is cancelled. Remember again student, this concept you can use this shortcut tricks only if you want to discard the options. Second method, how you can use the second method? So I can use the Mn test. So that means supremum of all those x from 0 to infinity of the gnx minus 0, that is my gnx. Fine. Now clearly say if I consider this number is my y. Fine. If you take y dash is 0, fine. So clearly say you will get x is my 1 over n. How I can directly find that? You can substitute denominator part as a 0. Because what is that limit? What is the y dash is 0? What is the meaning of that? This is my critical point. What is the definition of the critical point? All points where y dash is 0 and all those points where y dash goes to the infinity. So when the y dash, if I call this is my y, when it will be infinity, when this part will be my 0. So I can ignore the plus minus sign. So clearly say if I add 1 over n, and clearly say 1 over n also lies in this case, only plus 1 over n. So what is the mn? That is 1 over 1 plus 1, which is not 0. So therefore not converges uniformly. Again this option is cancelled. A option is the right answer of this problem. Don't forget to like and comment on this video. Okay, look at this another one. E is the collection of all those elements of the natural numbers which are of the form 1 over n. Fine. Define the sequence fm which are given to be this. Then their converges, subsequence converges. So your target is to find limit of this case. Fine. Now clearly say again I can use the subsequence concept. I can found a one natural number n such that x will be greater than equal to 1 over m, because this number is my 1, 1 over 2, 1 over 3, 1 over 4. I can found some number x whose answer will be greater than of this case. So that means fm will be my cos mx, because whenever x is my greater than equal to 1 over m, this is my case, so it will be my cos mx. So clearly say, can you find the limit of this? Limit does not exist. Fine. Or you can say it depending upon that if x is equal to pi by 2, or if x is equal to 0, then cos 0 is my 1. Fine. Otherwise it has some another number which lies between -1 to +1. Fine. So clearly say this is my discontinuous function. Now look at that. No subsequence converge, no subsequence. That's wrong, because if I choose the subsequence as say 1 over m, then what is the answer of this? If x is 1 over m, so it is only my cos of 1, which is a unique answer. Fine, then it converges, but he said no subsequence. This option is cancelled. Every subsequence, now look at that, every subsequence converges at every point. That's a wrong statement, because you can see the limit point is my minus 1 comma 1, so limit does not exist. So this option is also cancelled out. There exists infinitely many subsequences that converges at every point. Yes, for the different value of the x, you can choose 1 over m, you can choose 1 over 2m and so on. You will get the infinitely many subsequences. There exists a subsequence, fine, which converges to the 0. This is not always. Why? Because you can see there is a subsequence which converges to the cos of 1, which is my non-zero, but he said which converges at every point. And you can say this option is cancelled. C is the only option which is right. Now again you can see this is the 2024. Sequence is defined and limit of the fn. So can you find the limit of the fn? Again, you have the two cases. X is 0 and x is my non-zero. Dear student, what if you calculate the limit, that means you are talking about the point-wise convergent. And if you want to know more detail about the point-wise convergent, I always recommended you must watch about my this example of the point-wise convergent. More than 20 examples in this lecture you will find that. If x is equal to 0, what will happen? 0 over 1 over n, that is my 0. If x is non-zero, what is the limit of this? X square divided by x square plus 0. That will be x square over under root of x square. That means x square over mod x. That will be mod x. Fine. And clearly say it is a 0 for all x. Wrong. It is for x for all x. Wrong, because x equal to 0 is 0, otherwise something. And mod of x. Yes, I can write this quantity also as a mod of 0. So that means fn converges to the mod of x for all. Limit does not exist. That's wrong, because the limit is existence for all the cases. So the right answer is D is my correct answer. Don't forget to like, comment and subscribe my YouTube channel. Okay, again they are talking about the pointwise convergence. So your target is to find limit as n approaches infinity. Your domain is closed interval 0, 1. I can consider three cases. X is 0, x is 1, x is lies between 0 and 1. If x is equal to 0, this limit is my 0. If x is equal to 1, this will be my 1 log of 1 plus 1 over 2. So that is a log of 1, and log of 1 is my 0. If x is lies between 0 and 1, then the first quantity, this will go to the 0. So the limit is my 0. Fine. So what does it mean? That means fn converges to the 0 pointwise, because the limit is existence in all the cases. The limit is existence. Once the limit is existence, it is a pointwise. The first option is the correct option. Now, second option, converges uniformly, converges uniformly. So I can define the Mn. Mn is supremum of x belongs to the 0, 1 of fx, fnx minus fx. Fx is my 0. It is my x raised to power n log of 1 plus root x over 2. Fine. Now, what is the supremum of this? Assume that the supremum is occurring maximum at 0. What will happen if x is equal to 0? This limit will go to the 0. If the supremum is occurring at x is equal to 1, then again log of 1 0, again it goes to the 0. If the supremum is occurring in between the 0 and 1, that means say for example 1 over n. Fine. So what will happen? Occurring between 1 over n, or you can say n over n plus 1, or you can assume as 1 over 1 plus n, any are there, fine. But this number is outside of this, so I can take it as a 1 over 1 minus 1 over n. Otherwise, you can take this number as a y and taken as a first derivative 0. Moreover, you can also think like this function, if I consider this is my y, which is increasing one, fine. Otherwise, no issue, I can start with this case. If I substitute this value, it is 1 over n, fine, into log of 1 plus 1 over 1 plus 1 over n divided by 2. Now what will happen if n approaches infinity? This value will goes to the 1 over e. This number goes to the 1. 1 plus 1, 2. 2 divided by 2, 1. Log 1 again 0. So in all the cases, the limit will goes to the 0. Hence, mn goes to the 0. What does it mean? Fn converges to the f uniformly on the closed interval 0, 1. He said not on the uniform close, not on the uniform close. So the right answer is A and D are my right. Okay, look at this another one. Fn is a sequence of the continuous such that Fn converges to the f pointwise and f is my integrable. Fine. Then your target is to check whether, okay, first of all, firstly I will give you the tips. Fine. If Fn converges to the f uniformly on the closed interval a comma b, then you can say limit from a to b Fn x dx converges to the limit a to b fx dx. Fine. If Fn converges to the f uniformly on the closed interval a comma b, then this hold, while converse may not be true. Secondly, if instead of this Fn converges to the f over this interval, say a comma infinity, fine, then this quantity may or may not hold. May or may not hold. Fine. Now based on this simple shortcut tricks, how you can see that this is an integrable function. And if you watch about my this lecture of that is an integrable. Where is the integrable lecture? This is the uniform convergence and integrable lecture. If you watch about this lecture of the integrable, you can see already this kind of example I have explained. Now, firstly we will see about this case. Fn converges on the 0 comma infinity. Fine. This implies I need a 0 to 1 because 0 to 1 is a subset of this. I can say Fn converges to the f on the subset of this also. That means uniformly. Now based on this simple tips, if Fn converges to the f on the closed interval, then this part will be satisfied. Look at this case. If Fn converges to the 0 comma infinity or a comma infinity, then this may or may not be hold. Fine. Now look at the first one and the second one. Because in the first case it is not given that it is a uniform convergence, so definitely this is not true. Or moreover, this is not the closed interval. Anyhow, I will instead of that you can provide some example. So you can consider the Fnx is say n if x is lies between 1 over n and 0 if x is greater than 1 over n. So can you find the limit of the Fn as n approaches infinity? So what will happen? So clearly say it is my 0. Fine. If n approaches infinity, this limit will be my 0. Fine. So this value will be my 0. Clear? And clearly say f of x is my 0, which is my integrable. Now, does this condition hold? What is the left hand side? 0. What is the right hand side? Instead of taking 0 to infinity, this limit will be my 0 to n of the n plus 1 over n to infinity. So what is the answer of this limit? 1 plus 0. It is my 1. So this limit is my 1. This limit is 0. So clearly say they are not equal. Similarly, for this case, if I consider same example, or you can simplify it, instead of I can say this is my 1. Fine. So what is my fn? Fx will be again fx. So the difference will be goes to the 0. Fn will goes to the f on the interval 0, 1. It's satisfied. This example, does it convergent uniformly? Clearly say this function is my discontinuous function and fn converges to the f pointwise. It is given to you this f is my discontinuous function. So what does it mean? Fn does not converges to the f uniformly. So this option is also cancelled. Right option is only B is my right. These are same thing are there. The converse may or may not be true. Okay, look at this another one. Xi n is the sequences of the function which are defined this. G and H are the limits supremum and infimum. Very simple. Again, is a very simple. What is the meaning of that? G of x is equal to hx is equal to 1. What does it mean? That means limit of the supremum of the xi n, which is equal to the limit of the infimum of the xi n, which is my 1. What does it mean? This means xi of n converges to the 1. Fine. It is my convergent because limit infimum and supremum are same. What does it mean? It means there exists some x such that xi of nx is my 1. Fine. What does it mean? According to the definition, when it will be the 1? When x belongs to the a of n. And you can see the same thing they are asking. Similarly, if you look for the last option, both are my 0. That means if this is my 0, this is my 0, it means this converges to the 0. It means there exists some x which converges to the 0. That means x does not belong to the an. So this option is also correct option. Now look at the third option. If g of x is my 1, h of x is my 0, what does it mean? Limit supremum is not equal to the limit of infimum. That means the sequence xn is not convergent. Fine. So if it is not convergent, then you can never say that x belongs to the ak always. Fine. You can never say, but he said x belongs to the ak always. So this option is cancelled. Look at this third option. Again, gx and 1. Then there exists a sequences of the distinct integers such that that's a subsequence. They are talking about the subsequence. Yes, because if the sequence is not convergent, we can find the subsequences of the a and k such that whenever x belongs to the nk, this xn converges to the 1, and for some another x, this xn converges to the 0, because for the some subsequences. So therefore, yes, this is my correct option. So the right answers are A, C and D are the correct options. Okay, look at this another one. Fn is the sequence of the continuous function. Fn converges to the f pointwise. Fine. So as I told in the previous example, this does not hold always. This only hold on the closed interval, but these are not closed interval. Again, the same example you can define it. N when x lies between 0 to 1 and 0 if x is greater than 1 over n. So this option is cancelled. Second option, Fn converges to the f uniformly. Fine. But again you can see the intervals are not closed. Fine. If the intervals are not closed, then this is may or may not be true. This option is also cancelled out. Look at the third option. Fn converges to the f uniformly. Fine. Also, Fn is my continuous function. So what is the property of the uniform convergence? What is the lecture of the uniform convergence and continuity? What is the this lecture suggested you? This lecture suggested you this f must be continuous. Fine. This result hold only if it is my uniform convergent. Make sure student, if Fn converges to the F pointwise, fine, and this Fn is my continuous, then this F may or may not be continuous. But if Fn converges to the F uniformly, then Fn is my continuous. This implies F must be continuous. Yes, this option is my correct option. There exists a subsequence, there exists a sequence of the continuous function, so that limit does not exist. Yes, again the same example you can choose. Fn x is my 0 is less than of 1 and x is my greater than 1. Fine. So clearly say on the left hand side is my 1, this is not 1, which is satisfied. So because this is not equal to, then definitely it is satisfied. So correct options are my C and D are my correct answer of this problem. Okay, look at this another one. Gnx is defined as a sine square x. Fnx is my integrable function. 0 to x, g of n. Fine. Then they are talking about the fx. So fn converges if and only if gn converges. Fine. Now we can check about only for the gn. So firstly, pointwise. What is the limit as n approaches infinity of the gx? So we can consider two cases. If x is my 0, if x is my non-zero. If x is 0, this limit will be my sine square 1 over n. And if you take n approaches infinity, sine 0 is my 0. If x is my non-zero, then you can take an n approaches infinity. This value will be my sine square x. Fine. So I can combine them, which is because sine 0 is 0. So I can say g of n converges to the sine square x for all x belongs to the domain 0 comma infinity. That means it converges pointwise. The first option converges pointwise, fine, but not converges uniformly. We will see does not converges pointwise close uniform convergent. Now for the uniform convergent, I can calculate the Mn supremum of all those x from the 0 to infinity of the Gnx, that is a sine square x plus 1 over n minus sine square x. How you can solve that? I can use the formula of a square minus b square. So that will be my sine of a, sine that is a minus b, a plus b. Fine. A plus b. Now let me clear this. Now we all know what is the formula of the sine a minus sine b, which is always be less than or equal to a minus b. Fine. So I can use this inequality, which is less than of a minus b, that is a 1 over n into sine of x plus 1 over n plus sine of x. Clearly say this function is my bounded, and as n approaches infinity, this will goes to the 0 because this is my bounded function. So what does it mean? Mn goes to the 0, therefore Fn converges to the F uniformly on the domain 0 comma infinity. Fine. So the first option said not uniform convergent. So this option is cancelled out. Last option is correct option. Now if Fn converges to the F uniformly, then it's also uniform convergent of the subset, and 0 comma 1 is the subset of this. So yes, this option is also correct. C and D are my correct answers. Okay, look at this another one. T and A are the positive real numbers. Which of the following statements are my correct? Very, very simple. What I teach you in my all those previous PY question series. Because A is my unknown, you can freeze the value of the A. Fine. N I can choose it as a 1. Fine. So this B is my B of 1 because A is my 1. collection of all those x in my R such that x square is less than equal to 1. Fine. Now look at the first option. First one is integration of the b1 f of tx dx. Is it equal to b of t into a? What is a? A is my 1, so t into 1 is my t. F of x and n is my 1 minus 1 of dx. So let's start. What is the f of tx? What is f? F is any continuous function. So you can substitute it. Tx is my y. What is the dx? dy over t. So what is the limit of this f of y into dy over t? What is the domain is? In this case, what is the b1? b1 is my minus 1 to plus 1. So if x is my minus 1, it's a minus of t to plus of t. So what will happen? And if you look about this case, what is the b of t? Minus t to plus of t, f of x, t raised to power minus 1 into d of x. Clearly say both are same. So yes, this option is the correct option. Look at the second option. Again, I can simplify this firstly. That is a ba minus 1 to 1 f of, or you can fix as a t also. Say t is my 2. That's on your choice. Fine. So tx of dx, it is, what is that? B into t of n into a. What is the n? N is my 2, a is my, n is 1, a is 1, so multiply is my 1, multiply by t, this is basically of b of t, minus of t to plus of t, fx into t of dx. Are they equal? No, because if you consider this is my y, then dx will be dy divided by t, but it is written in the numerator. So this option is also cancelled. Look at the third option. Collection of Rn. N is my 1. So collection of only of R, x plus y of dx. Does it equal to the fx into dx? Yes, definitely. If you consider x plus y is my z, what will happen? Dx is my dz. If you substitute this equation, it is my fz into dz. And you can see both are my same. Again, this option is cancelled because n is my 1. Fine. But if you consider this is my y, then dx will be my dt upon dy upon t. But it is my in the numerator. So this option is cancelled. A and C are my correct answer of this problem. Okay, look at this another one. Fn is a sequence of the continuous function. Identify the correct statement. Fn converges to the f pointwise. Fine. Then this limit Fn converges to the 0 to infinity f. As I told you previously, if it is a pointwise and the domains are not closed interval, so first option is definitely cancelled. Second option, if Fn converges to the f uniformly, fine. Again, the domains are not my closed interval, so this option is cancelled. Third option, if Fn converges to the f uniformly and Fn is my continuous function, then f must be continuous function. Fine. So third option is correct option. Next one, there exists a sequence of the continuous function so that Fn converges to the f uniformly on the closed semi-closed interval, then and the limits are not same. That's true because this is not the compact set. Fine. If it is not a compact set or the closed interval, then this may or may not be equal. Fine. And the same suggested you, yes, 3 and 4 are the correct answers. Okay, look at this is a June 2023. Which of the following sequence is the convergent? So firstly, check about the pointwise convergence quickly. Okay, this is the first method. Fine. On the interval 0, 1. So if x is lies between 0, 1, what is the limit of the xn? 0. Fine. So that means Fn converges to the 0 pointwise. Does it convergence uniformly? I can define the Mn, supremum of all those x in the open interval 0, 1 of the xn. So what is the supremum? 1, which is not goes to the 0. So this option is not uniform convergent. This is not convergent uniform. Fine. What is the second method? As I told you, this is the first method. What is the second method? To discard the options, you can take an as a subsequence. Fine. From this domain, take any subsequence in this domain, 1 over n, or you can choose an as a 1 minus 1 over n. That's on your choice. And then you can define the subsequence. If it does not goes to the 0, then you can say the sequence is not uniform convergent. So what is that? X raised to power n. So 1 over n raised to power n. What is the limit as n approaches infinity? It does not goes to the 0. Or if you taken this series, then it will be 1 over, it is 1 minus 1 over n raised to power n for the subsequence this. Clearly say this limit is my e raised to power minus 1 as n approaches infinity, and clearly say this is not goes to the infinity. So again the first option is cancelled. Look at the second option. Again it's a uniform convergent. You can firstly check about the pointwise convergent. Again on the interval 0, 1, what is the limit of this case? As limit n approaches infinity, this part will be the 0, this is infinity, so that means this will be the 0. Fine. How you can check about the uniform convergent? Either you can define the subsequence or you can apply the amend test. Fine. Over the log n plus 1. Fine. Over the domain 0, 1, because my domain is 0, 1. Now clearly say what will happen, because it's a we have to take the supremum over the x. So 1 over log n plus 1 is outside. So what is the supremum of x raised to power n? This is a 1. So the limit is 1 over n plus 1. Clearly say this will go to the 0 as n approaches infinity. So yes, this is my uniform convergence. Fine. If you are using the second method on this problem, what will happen? You can define the subsequence, say 1 minus 1 over n. So then what is my f of x and k? So it will be, if you taken the limit, it is e raised to power minus 1 log of n plus 1, again which goes to the 0. So once it goes to the 0, this means it is my uniform convergence. Look at the third case. Clearly say when x is lies between 0 and 1, if you taken the limit as n approaches 0, infinity, it's a 0. If you apply the amend test, it is x raised to power n over 1 raised to power n over the supremum. Fine. X belongs to the 0, 1. Clearly say which will goes to the 1 over 2, because x raised to power n is a e. Fine. Or the maximum value is occurring at x is equal to 1 over this interval 0, 1, which is not 0. So therefore it is not uniform convergent. Fine. If you apply the second method, you can define the subsequence 1 over 1 minus n, and clearly say f of x and k, or the subsequence, this value will goes to the e raised to power minus 1. Denominator value is also goes to the e raised to power minus 1, which is not goes to the 0. Therefore it is not uniform convergent. Look at the last case. Clearly say it is a cos to the 0. If you apply the amend test, it is a supremum of x raised to power n 1 plus x n of this over the domain 0, 1. So clearly say the supremum is occurring at x is equal to 1. If you taken as x is equal to 1, it is my 1 over, and it goes to the 0. Therefore it is uniform convergent. Second method, if you consider the subsequence, again x is 1 over 1 minus n. This value will come to e raised to power minus 1, 1 plus n e raised to power minus 1. So that will be 1 over e plus n. Clearly say it goes to the 0 as n approaches infinity. So again, yes, this is the right answer. B and D are my correct answer of this problem. Okay, look at this another one. Again, they are talking about the pointwise, pointwise, pointwise. They are talking only for the pointwise. What is the limit of the Fn? domain is my 0, 1, open interval 0, comma 1. If x is equal to 0, the value is my 0. If x is equal to 1, what is the limit of n approaches infinity minus 1 raised to power n? Clearly say the limit does not exist. Fine. So that means this is does not exist. So once the limit does not exist, what does it mean? This means this is my not pointwise convergent. Once it is not pointwise convergent, that means it is my not uniform convergent. So there is no pointwise convergent subsequence. Convergent subsequence. Converges pointwise everywhere. That's a wrong statement. Subsequence. Fine. Now, and if in the given statement they are asking about the uniform convergent, then we can say it's not a uniform convergent. Now subsequence, there exists a pointwise convergent subsequence. When it will be the convergent? If the limit is my unique, fine. So I can choose the subsequence is my 2 of n. This is my subsequence, fine. And clearly say this is x raised to power 2n. And if you want to calculate the limit over the cases x is 0, x is 1, x is lies between 0 and 1. What will happen? If x is 0, answer is 0. X is 1, answer is 1. If x is 0 and 1, it's my 0. So you can see it is my existence. So therefore, f of 2n, that's a subsequence, converges to this function f. That means subsequence converges pointwise. So there exists, yes. Fn has no pointwise subsequence. Cancel. Fine. Now look at the last one. It has exactly one pointwise. So one we have obtained. If what will happen if we consider as the odd series? Fine. So what is the odd series is? 2n plus 1. So what is the negative sign of the odd series? Minus x raised to power 2n plus 1. And if you take on the series, again x is 0, x is 1, x lies between 0 and 1. If x is 0, answer is 0. If x is 1, answer is 1 and 0. Again you can see this is existence. This is my minus 1. Fine. It is existence. So that means the second subsequence, this is the second subsequence, f of 2n plus 1. But he said exactly 1. This option is also cancelled. A is my right. Okay, look at this another one. The sequence of the function fk, I can write this in terms of the n. X raised to power n, 1 plus x of square. Fine. Instead of the k, I can replace as a n. Which of the following is the bounded variation? Is found. Okay. Firstly, we will tell about the uniform convergence. Okay. I think that's quite easy because my domain is 0, 1. Fine. If I again consider the subsequence, this is my subsequence of the 0, 1. And if I found this, what will happen? It's e raised to power minus 1, 1 plus x square. It doesn't go to the 0 as n approaches. So that means it is my not uniform convergent. Fine. So it does not converges uniformly. Fourth option, cancel. Now, look at this. For every k, this integration is finite. So k means n. If I choose n is my 1. So what is the integration of 0 to infinity f1? X over 1 plus x square. Fine. Definitely this limit does not exist. Why? If I plus 1 and minus 1, then clearly say this is my separate part. Fine. Now if you integrate them, it will be my log of 1 plus x over the domain 0 to infinity, and it will be my minus 1 over 1 plus x from 0 to infinity. Clearly say if you substitute as infinity, the limit goes to the infinity, but he said less than infinity. Fine. Now look at the first option. For each k, the function is my bounded variation. What is the meaning of the bounded variation? If you calculate the derivative, it is my bounded. Fine. And clearly easily say that for each k, for example, if I choose n is my 1, Fine, what will happen? Or if you find the derivative with respect to the x, what will be happen? Because on the compact interval, once you are taking the compact interval 1 plus x square, sorry, with respect to the x. So if you consider with respect to the x, 1 plus x raised to power 4, 1 plus x square into n of xn minus 1 and minus twice into x raised to power n. Now if you consider the modulus value, and because my domain is the compact interval, any interval you can say a to b, so definitely this is my less than equal to n. So this option is definitely correct. Now integration of the 0 to 1 fk x raised to power k, that's I consider as in terms of the n over 1 plus x raised to power n. Fine, as the limit n approaches infinity. Again a very simple, because sorry, this is my 2. So if n is my greater than 2, fine, then you can use the partial fraction. So I can use an, if n is my 3 for example, then what you can do, you can separate them x plus something, fine, and because the limit is my 0 to 1, so this limit is my finite, integration of limit is my finite over this domain, because this part is my integrable. Once this is integrable, definitely your answer will be my finite. So yes, this answer is always existence. Okay, look at this another one. C0 is the space of all those continuous function on the R such that limit is my 0. C0 is equipped with the norm, is a uniform convergent. Which of the following properties are my correct? Very, very simple. Just try to read the statement very carefully. Fn converges to the F on the compact set. Fine. Then your target is to prove Fn converges to the F on the R. That's a wrong statement, because if it is a compact on the R, then you can say it is a uniform convergent of the subset, but you can see R is not the subset of the A comma B. So this may or may not be true. Fine. So first option is cancelled. Look at the second option. What is the second option? This means, that means Fn converges to the F on the R. Why? Because norm is defined on the R. So Fn converges to the F on R uniformly, and because compact set A comma B is a subset of the R, so definitely Fn converges to the F uniformly on the subset of the R. Fn converges to the F on the compact set if and only if. That's wrong. As I already told you, the example is n and 0. Fine. Otherwise, neither of the statement implies the other. That's wrong. If Fn converges to the F uniformly, then you can say it is correct. Fine. If you want to find the another example, I will provide you another example also. Let's say f of x is my n is any function, sequence of the function, say x over n, and x is my a comma b. Then what is my fx? What is the limit as n approaches infinity? So clearly say it is my 0. Fine. Then if you apply the Mn test, that means supremum of on the compact set of the x over n, which is less than equal to b over n, and it goes to the 0. Fine. So that means Fn converges to the F uniformly. This example, uniformly on the a comma b. But if you consider on the real line R, what is the supremum of the, what is the supremum over the R? Clearly say it is not goes to the 0. So therefore, this is the counter examples. This is a single counter example to discard the options. Okay, again they are talking about the pointwise convergence. So collection of all those x in the R. X is 0, x is non-zero. If x is 0, the sequence limit is my 1. If x is non-zero, then the limit n approaches infinity is my 0. Clearly say both the limits are existence. Therefore, Fn converges to the F pointwise. Fine. But you can also see that this function is my discontinuous. Fine. So if this function is my discontinuous, what does it mean? Fn does not converges to the F uniformly on the closed interval 0, 1. This option cancel, this option correct. Pointwise satisfied, continuous function satisfied. Fine. Now, does it converges uniformly on the closed interval half, 1? Now you can see that here the function is discontinuous at the point x is equal to 0. Fine. And 0 is the part of this. Now you can see, is this function f is continuous on the half, 1? Yes, because on this interval half, 1 the function is my continuous. Fine. So that means this function may or may not be uniform continuous. So how you can check about the on the interval half, 1? I can apply the MN test. Supremum over the half, 1 fx 1 plus n square x square. How you can find the supremum of this? The supremum will be when this number will be minimized. When this number will be minimized, when x will be minimized, what is the minimum of the x? Is my half. Fine. Because half lies in this. If you think about that, x is equal to 1 over n. Does 1 over x, 1 over n lies between half, 1? No. So that means x is equal to half, 1 over n is not the maximum point. So x is maximum only at the half. So what is the value at the half? This is n square over 4. That means 4 over 4 plus n square. Clearly say it goes to 0 as n approaches infinity. Yes, this is my uniform convergence. Fine. Now, look at the last option. Again, because the function is not uniform convergent, then this may or may not be true. But if this function is uniform convergent over the interval 0, 1, then this is definitely true. For example, if instead of this statement, if they are asking about 0, half to 1, half to 1, because the function is uniform convergent, then this is automatically true. But in this case, they are talking about the 0 to 1. Fine. Now, what is the, on the left hand side, what is the answer of this? This number is my fx. Fine. On this interval 0, 1, what is my fx? 0. So the right hand side is my 0. What is the left hand side? If you look about the integration of 1 over 1 plus n square x square from 0 to 1. What is the integration of this? It is my tan inverse nx divided by n from 0 to 1. What is the limit of this? Tan inverse n over n, and tan inverse 0 is 0. Now you can compute the limit as n approaches infinity. It is infinity by infinity form. Sorry, tan inverse infinity is a pi by 2. Pi by 2 over infinity is my 0. So once is a 0, right hand side also 0. So yes, these are my correct option. A, C, D are the right answer of this problem. Let C of C is a function which are defined on the R to R, which are defined as a continuous. There exists a compact set such that f of x is my 0 for all those x which belongs to the k complement. Fine. That means if this is my set, fine, this is my k, outside this domain fx is my 0, and inside this domain the function is my any continuous function. Define g is my e raised to power minus x square for all those x in my R. Which of the following statements are true? There exist. You can see they are talking about the there exist. There exists a uniform convergent sequence. Yes, you can define the Fn. You can define the g of x. If x is lies between, it is on the n, I can say any of the closed interval. So say mod of x is less than of the n. Fine. Otherwise 0. Fine. Clearly say this function Fn converges to the g pointwise. Fine. Also Fn converges to the g uniform. Fine. So that is the correct answer. there exists, again there exists a sequence which converges pointwise. Same example. Fine, because we have proved that it's a there exists. So yes, this is the right answer. If the sequence converges pointwise, if the sequence in the Fn converges to the G pointwise, then it must convergent to the uniformly. The word is the must. That is wrong. Fn may or may not be the converges uniformly. Fine, so this option is cancelled out. However, the converse is true. If somebody say sequence converges uniformly, then it must converges pointwise. That's the correct statement. There does not exist any sequence which converges pointwise. That's wrong, because we have obtained the second part. There exists a subsequence. Okay, look at this another one. Consider the sequence Fn converges. Okay, fine. Fnx. Firstly, we will check whether the pointwise convergent or not. X belongs to the 0, 1, and x lies between 0 and 1. If x is 0, 1. If x is equal to 1, limit is 0. If x is 0 and 1, the limit is, if I say 1 over n, so limit is 1 over 3. Clearly say the limit exists, but they are not continuous. Fine. If they are not continuous, what does it mean? Fn converges to the f pointwise, that is a fine. But because this f is my discontinuous, what does it mean? Fn does not converges to the f uniform. So the first answer is no. The second is, first is my false, second is, first option cancelled, second is the correct answer. Fine. There is one more method. What is that? How you can check about the subsequence? You can define any of the subsequence in between the 0 and 1. I can say 1 over n. Then what is my f of nk? 1 over 2 plus 1, which is not goes to the 0. That means it is not uniform convergence. Look at the g and x. Again, they are talking about the 0 to 1. If I choose the subsequence as 1 over n, then g of x and k is 1 over n. 2 plus 1, that means 1 over 3n. It goes to the 0 uniformly. So yes, this option is my correct option. Second, if you define the limit of the gn, second method is, what is the limit? If taken 0 and 1, if x is 0, answer is 0. If x is equal to 1, then it's a 1 over 2n plus 1. It is my 0. Fine. And if x is lies between 0 and 1, then again it is my 0 because of this value. Then if you define the mn, that is the supremum of x divided by 2nx plus 1. So clearly say the maximum is occurring at 1 over 2n. If I consider maximum is 1 over 2n, I can substitute this value. What will happen? Let me clear this. This limit will be 1 over 2n divided by 1 over 2n. That's 1 plus 1, 2. That means 1 over 4n. It goes to the 0. Yes, this is my uniform convergence. Both are true, false. So the right answer is B and C are the right answers. Okay, let Fn is a sequence of the real valued function. Suppose it converges to the continuous function. Fn converges to the f uniformly. It is given to you already on the uniform on the closed and bounded interval. This is given to you as a continuous function, sequence of the real. So it may continuous or not. Which of the following following statements are correct? Okay, on the closed interval, I can define the sequences. Look at that. Fn is a continuous or not? It is not given to you. They are only the sequence of the real valued function. I can define the sequences x1 over n on the closed interval a comma b. So clearly say this Fn converges to the f uniformly. Fine. On the closed interval, because the supremum is the supremum of x over n goes to the 0 over this closed interval. Now this property is satisfied. Now sequence Fn converges on the R. Does this sequence of the function converges uniformly on the R? No. Why? You can see if I consider x belongs to the R, is not goes to the 0. Fine. First option, cancel. Now, the sequence Fn converges pointwise. Definitely, because Fn converges to the F uniformly, Fn converges to the F pointwise is my final. For the sufficiently large n, the function is my bounded. For the sufficiently large n, the function is my bounded. So clearly say, if I consider Fn is bounded on what? It is not given to you on the closed interval. That means they are talking about the R. Fine. So clearly say, if you consider again this example, whenever n is a very, very large number, but Fn is my not bounded. Why? Because you can see what is the f of n, x over n. On this R, x is not my bounded. It is not less than of the 1 over n. So that means it is not bound. For the sufficiently large n, the function fn is continuous. This is a continuous. Fine, because this is my polynomial. Fine, but based on the one counter example, we can't correct the option. So now look at that. My fn is may or may not be the continuous. Fine, so I can define the function easily. How you can define the function? I can define the function 0. Function is 1 over n. You can choose any number, say 0, and 0 is less than of 1 over n. Fine. So clearly say this function is my not continuous. Is it continuous? No. But what is the f? If you consider the f will be 0, because if you consider the limit as n approaches infinity, this number will be my 0. Every constant number is my continuous. It satisfies this property. Fn converges to the f uniformly. That's also fine on the closed interval 0, n by 2, fine. But it is not continuous. So the right option is only B is my right answer. Don't forget to like, subscribe and comment on this video. Fn is defined to be this: pointwise convergent, uniform convergent, and so on. So firstly find the limit as n approaches infinity. N plus 2, n plus 1, t raised to power n of 1 minus t. Fine. How you can find that? Now clearly say, what is the domain? Domain is my 0, 1. So that means if I consider t is my 0, t is my 1, t is lies between 0 and 1. If t is equal to 0, answer is 0. If t is equal to 1, what will happen? If t is equal to 1, what is the limit? If t is equal to 1, 1 minus 1, 0. And if t lies between 0 and 1, this component is 0, but this part is infinity. So I can apply the L'Hopital rule. I can write this quantity is my t raised to power minus n. Then it is infinity by infinity form. Then if you take the derivative, it is my 2n plus 3 over t raised to power minus n log of t into minus 1. Again it is infinity by infinity form. Again I can apply the L'Hopital rule. It is t over minus log of t square. So it goes to the 0. So therefore this f of n converges to the f pointwise. Fine. So fn converges to the pointwise, fine. Fn converges uniformly, that we will need to check. Now, how you can check about the uniform convergence? So for the uniform convergence, I can apply the Mn test, supremum over the domain 0, 1, n plus 2, n plus 1, t raised to power n, 1 minus t. Fine. Now, how you can find the supremum of this? So I consider this value as my y. I can differentiate this with respect to t and put them as a 0. So because this is my constant which is outside, so it is my t raised to power n of minus 1 plus n into t raised to power minus of 1 minus t. If I substitute them as a 0, t raised to power n will be cancelled out. It's a minus 1 plus n over t into 1 minus t is equal to 0. So if you open that, it's a minus of t plus n minus n t is 0. So t value will be n over n plus 1. Fine. Now I can substitute this value of t is n plus into n plus 1 in this case. So you will get as n plus 2, n plus 1, n over n plus 1 I can written as 1 over 1 by n. And what is the 1 over? N over n plus 1 is 1 over n plus 1. Clearly say this number will be cancelled out. If you take a limit, so it will be infinity. This number will be my e. So that will go to the infinity, not goes to the 0. That means fn does not converges to the f uniformly. So B option is the correct. This option cancel. The sequence fn diverges. It is not a divergent. So this option, because why it is not divergent? Because we have computed the limit of the fn as f. So this is my 0, which is unique. That is convergent. So divergent is cancelled. Look at the last option. How you can see now this number is my f. Fine. And we have computed the limit is my 0. So the left hand side, the right hand side is my 0. How you can compute the left hand side? 0 to 1, f of n with respect to the t. I can take an n plus 2 outside, n plus 1 outside. T raised to power n, 1 minus t. What is that? This is nothing but my beta function. Fine. So what is the integration of this component? It is my beta of n plus 1, comma 2. How you can open the beta function? N plus 2, n plus 1 into n factorial, 1 factorial, and n. Okay, firstly I can tell you what is the beta function of m into n. This is gamma of m, gamma of n, and m plus n. And once m is my integer, we all know this is nothing but m minus 1 factorial. So m plus is n factorial, 2 gamma is my 1, m plus and n plus 3 I can written as a this number. So clearly say, if I open this bracket, this number up to this number is cancelled out. The only quantity which is left behind is 1 over. So it will be goes to the 0 as n approaches infinity. So this component is also 0. Yes, this answer is also correct. B and D are my correct answers of this problem. So you can see that these are the simple series which you have learned about that. For more detail, I again recommended you must watch about my real analysis playlist and the theory lecture about the sequences of the function. Once you watch all these my sequences of the function playlist, you will be more confident for solving any problem in a very simple manner. Apart from them, you can also see the playlist of the CSIR UGC NET, which contain all those PY questions series. I hope you can like, share and comment on this video with your friends. Don't forget to subscribe my YouTube channel. And thanks for the watching. Best of luck students. Happy luck.